Okay, we would like to find Laurent series for the function f of z equals 1 over z times z plus 1 on two different annuli. The first annulus is centered at 0 and has an inner radius of 0 and an outer radius of 1. And the second annulus, also centered at 0, inner radius of 1, outer radius of infinity. And these choices here for the annuli come from the places where this function has singularities. This function is defined and differentiable everywhere except z equals 0 and z equals -1. The obvious places that cause the denominator to equal 0. So in the complex plane, we have here 0, and here is -1. So if we make a disk, if we make the unit disk, then this function is analytic on the punctured disk, which is the same as the annulus here. A center 0, inner radius 0, outer radius 1. And then the function is also analytic outside of this annulus, which we could think of as another annulus, and that would be A2, which would be an annulus centered at 0 again, inner radius 1, and outer radius infinity. So we would like to create a Laurent series for each case. So there's going to be two different Laurent series, one which converges on the inner annulus and one which converges on the outer annulus. And the key is to use the geometric series 1 over 1 minus z equals summation k from 0 to infinity of z to the k. This converges if the modulus of z is less than 1. So we want to use this on the inner annulus. So our function, 1 over z times z plus 1, we can write as 1 over z times 1 over 1 plus z. And now we want this to look like this. We'll just make the plus into a double negative. 1 over z, 1 over 1 minus -z. Now we can make a Laurent series for this function, which is valid as long as the modulus of -z is less than 1. And the modulus of -z is, of course, the same as the modulus of z. So we have 1 over z times the summation k from 0 to infinity of -z to the k, according to this formula here, with -z in the place of z. And that's valid again as long as the modulus of -z is less than 1. And this is equal to 1 over z times the summation k from 0 to infinity, -1 to the k, z to the k. And we could write this as summation k 0 to infinity, -1 to the k. We'll bring this z in, so we have z to the k minus 1. Modulus of z less than 1. So if we wanted to think of this as a Laurent series with potentially negative powers, which this one does, when k is 0, you get a negative power. So to make that clearer, we'll start k at -1, and we'll just make this z to the k, and this power is 1 bigger. So we have this. And so in the long form, if k is -1, this is positive, we get 1 over z. If k is 0, we get a negative, and this is just 1. If k is 1, then we get a positive, and we get z, and then minus z squared, etc. So there is our Laurent series on the first annulus, because this is valid as long as the modulus of z is less than 1, which is the first annulus. Now for the second annulus. So we still want to use this formula in the upper left-hand corner. 1 over z times z plus 1. And we want this on the annulus that is outside of the unit disk here. That's a 0, 1, infinity. So in order to use this formula, the modulus of z in this second annulus, the modulus of z is greater than 1. The modulus of z is greater than 1. And so that's not going to work here. So if the modulus of z is bigger than 1, we need some variable quantity whose modulus is less than 1. Well, let's just take the reciprocal of this. 1 over z, the modulus of that, will be less than 1. So we want to express things in terms of the variable 1 over z. So here's our function. It's 1 over z times 1 over 1 plus z. And this is the one here that we would like to transform into a Laurent series, because this one's already centered at 0. This one is centered at -1. So what we're going to do here in order to use this formula is, with this variable, 1 over z, is we're going to factor out a z here. So this is 1 over z times 1 over z times, if I factor out a z, I'm left with 1 over z plus 1. So this is 1 over z times z is z squared, and then times 1 over 1 plus 1 over z. So there is the expression that we want. It looks like this, and it has the variable 1 over z instead of z. Of course, it has a plus where we want a minus, so we'll just turn that into a double negative. 1 over z squared, 1 over 1 minus -1 over z. So now we could use the geometric series formula on this. And so this is going to be 1 over z squared times summation k equals 0 to infinity of -1 over z to the k. And this is valid as long as the modulus of -1 over z is less than 1. So we have 1 over z squared summation k 0 to infinity, -1 to the k, z to the -k. And this is equivalent to saying modulus of 1 over z is less than 1 because the modulus of -1 is 1. And let's see if we could write this using negative values for the variable k. So we have 1 over z squared summation k equals -infinity to 0, -1 to the -k, z to the k. I just replaced k with -k so that all of these k values in the summation just become negative. Now, -1 to the -k just means 1 over -1 to the k, but that is the same as -1 to the k. So we have summation k goes from -infinity to 0 of -1 to the k, and it's z to the power k minus 2. And now I would like to have this just say z to the k. So when k is 0, we get a -2 here. So we could do summation k from -infinity to -2 of -1 to the k plus 2 times z to the k. That should be the exact same series as this one. And -1 to the k plus 2 is the same as -1 to the k. K goes from -infinity to -2, -1 to the k, z to the k. And this is valid as long as the modulus of 1 over z is less than 1, which is the same as the modulus of z is bigger than 1. And that is our second annulus here, a center 0, inner radius 1, outer radius infinity. And finally, let's just take this and write it in the long form. If k is -2, then this will give us a plus, so we get 1 over z squared. And this is going to alternate, so minus, and the powers are just going to get bigger and on the bottom. K is -3, so this should have been 1 over z squared. And then minus 1 over z cubed plus 1 over z to the 4th, etc. So this is equal to the function 1 over z times z plus 1, and it's valid when modulus of z is bigger than 1. So we had two different Laurent series expansions for this function. One of them in the annulus that contains the point 0 inside, that contains 0 inside but not -1. That's this first annulus. And then the second one is the outside.